everybody. I have the written part of the exam for you. This will be due at the beginning of the class on Thursday. It's 3 problems, okay? So it's a couple of short answer, and then there's a couple of short composition things, and then there's, kind of way back when we did that animal exercise. I think we're using a programming project. So just, can you write classes? Can you structure classes? Can you do inheritance and stuff like that? So I don't know. I won't even guess how long it will take you, but I don't think you'll run into any bugs with this one. So I'll pass these out and around. If you see anybody that comes in late, just make sure they know that they're pick up an exam.
Is there any authorized aid on the professor?
There sure is, and it's listed in gory detail on the front. So I did list it, but if you have any questions, let me know on that. Pretty much open whatever, except the web. I mean, you can't go and download stuff off of the web. All right, okay. Now back to content. We have 2 more lessons until spring break, and we are going to be talking about today the algorithms and how long algorithms take, and how I can get a much better result if I just tweak the algorithm just a little bit. And all of this was, was precursed by the Fibonacci, where we saw you do it one way, it's a mess. You do it another way, it works really well. And we have this way of analyzing the algorithms or the tasks or the structure or the storage or whatever. If we want to analyze the use of resources, then we have the big O notation. In review, we had the mathematical definition, which is kind of opaque. It's kind of hard to see. But the 2 things about big O is we don't care about constants, and we only care about in the long term. So when you run a program, there's always a little bit of overhead to run it, and then it's actually doing your program. So we're talking about after the overhead, after the input size is big enough such that, I don't know, the little bit of overhead that you have to do doesn't matter. So if it has to, and so n sufficiently large, and we don't care about constants, all we care is how the growth rate is related to the input size. Now we always call n the input size, but it could be anything. It kind of just means on what we are measuring. And so, for example, if I have something that's big O of n, all that means is that it's constant, or all that means is that it is linear time, that if you double the input, it will double the output. And okay, yeah, you got a little bit of overhead at the beginning, but n is sufficiently large that we only really care double the input, double the size of the input, double the time that it takes. And when we're comparing between 2 different algorithms, sure, one might be better than the other. One might take 1,000 seconds versus 2,000 seconds, and then if you double the input, it takes 2,000 versus 4,000 seconds, and they're just a constant away from each other. They're twice as fast. Sure, you'd want the one, but they're in the same family. We think about the same family. And how do they react when you increase the input size? This input size, sometimes it's pretty clear, like if you're sorting numbers, it's how many numbers are you sorting. If it's a Fibonacci sequence, it's the order to which you are calculating the Fibonacci sequence. And let's see. Yeah, so it's going to be in the program, you're going to have to define then what n is. Sometimes, then, programs have 2 different inputs, n and m, and you got to decide which one you're going to use. There are some concepts of the 2-dimensional big O of n, but really, you'd say, okay, if I've got 2 different sizes, okay, what input size do I care about? And then you characterize that. And then you could go back and analyze the other inputs. So if you have n and m, you could get that. We just use this as a generic variable to indicate the input size or the order of the Fibonacci or whatever you are changing the value of, and you want to see how changing that value relates to the overall performance. Most of the time, we're going to think about that as the time that the program or algorithm or function takes to execute, the time of execution. Sure, that's what we will be doing, and that's the most common thing, but it could be anything. Big O of n, this could be how much space does it take up? How much memory does it take up? So the big O is, the function is whatever you're trying to measure, whether it's time, whether it's the size of something, and it could, and we wouldn't use this in a programming class, but you could talk about the cost of something, right? With the cost of something, if I want twice as much, does it double the price? Sometimes if you want, a house that's twice as big, it quadruples the price or something like that, right? So you could use this. We don't typically do that. But big O then, whatever arbitrary function you're trying to characterize. Okay. So we call this linear time, and we had the best possible thing was constant time, which means if you change the input size, nothing happens. It's not at all related to the input size. Maybe that's a really long time. Maybe that's 16 years. So if I input 1, the output is 16 years. And if I input 2, it takes me 16 years. And if I output 3, it takes me 16 years. Still constant time, but yeah, okay, that's a lot. But this is all about how it changes in relation to changing the input. Then we've got, and I didn't leave enough space for it again. Order of log n. There's also, I remember last time I didn't leave enough space. And the implication is log base 2 of n here. But log base 2 of n. So you can have something of what? So this goes here. Order of n log n. So this is bigger, longer, takes more time than something that's n, but not much. Okay? Next we've got order n squared. Next we've got order n cubed. And there's some other ones you can imagine. But the last one is order to the n, call that exponential, and that is the worst possible algorithm that you might have. You know what thing that you've seen in 221 is an order 2 to the n problem?
In 221?
Yeah, that's digital logic, right? So 221, you deal with Boolean logic, and there was something that you did that got really expensive if the number of inputs increased.
Multiplier.
So what I'm thinking about, sometimes my questions aren't clear enough, right? Truth tables, right? If you did a truth table for 3 variables, no problem. Truth table for 4 variables, Truth table for 5 variables, come on. Truth table for 7 variables, no. Truth table for 10 variables? How many rows are in the truth table of 10 variables?
2 to the 10?
Yeah, 1024. That's a lot of lines, right? So writing a truth table, that is an order 2 to the n problem. And if n goes up just a little bit, it can really take you a long amount of time. You can probably think about things that just take a constant amount of time. But can anybody think of a task that takes order log n time? Log n time? I'll give you an example here. Let's play the guess 'em game. And so I'm going to think of a number between 1 and 100. Okay, I've got my number. So Franco, go ahead and guess.
8.
Nope. Guess again.
Oh, you want me to keep going? Okay. 10.
No,
68.
no.
42.
Okay, we'll end it there. But how many on average would he have to guess?
50.
50. So you'd have to do 50 guesses. Now, if I did 0 to 1,000, and then we did that same guessing game, it'd take about 500. I upped it by 10, order of 10, and then the number of guesses would go up by a number of 10. That's order n. Okay, you probably didn't think that that's what I was going to do, but Sam, yes?
Would binary search also fall into that category?
Exactly, that is exactly right, binary search. So let's do an example, and Sam, you're gonna help me. Now, got my number. Yes,
Okay, what's the, is it?
0 to 100, yes.
50,
Too high,
25,
too high,
12,
too low,
18,
too high,
15,
too low,
16,
too low.
17.
There it is. Okay, so you saw that it took a lot less than 50 guesses there. Why? Because I told them if it's too high or too low. And if you guess in a reasonable fashion, what do? You slice the thing in half each time. So if okay, let's do, let's see how long it takes. 0 to 1,000. All right, Sam. 0 to 1,000.
500,
Too high,
250,
too low,
425,
too high,
350,
too high,
300,
too low,
325,
too low,
340,
too high,
330,
too low,
335,
too high.
333.
That's it. 10 guesses. So with playing the game with the way I did it with Franco, it would take 500 guesses. But I upped it by an order of magnitude, 10 times the range, right? There were 10 times the numbers to choose from, and we went up by about 3 guesses, right? And that's the binary search. It's kind of, I don't know if you guys have to do this anymore, but when you were looking for something in the dictionary, that's kind of what you did. You kind of turn to a page, you're like, that's too high, you take half of the amount of pages that you move that way, and okay, that's too low, and you would always split the number of pages in half every time till you got close. And so that's the whole idea of the high-low game, and that is, well again, now the more numbers I choose, the larger the range, certainly the more numbers, the more guesses it's going to take you. So it's not constant time at all. It does relate, but it doesn't relate all that much. I'll bet, so if we did 1,000,000, yeah. So if I did 0 to 1,000,000, 0 to 1,000,000, and you guessed pretty well, how many guesses do you think it would take? You split it in half every time.
With the binary guess?
So it's too high, too low. That's what I'm going to say. So 0 to 1,000,000, I'm going to pick a number in my head, and then you split it in half every time.
Maybe like 30?
20.
20?
20 guesses. 0 to 1,000,000, you should be able to get it in 20 guesses, about 20 guesses. And that's because 2 raised to the 20 is about 1,000,000.
Oh,
And what about if I did 1 billion? 0 to 1 billion. It'd take you 30 guesses. Yeah. So 0 to 1 billion is 30 guesses. You can make the input big, 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 huge, and the number of guesses only kind of goes up slowly. This is just the opposite, right? Just like the truth table, just one more doubles your work. And is one more than that, it's going to double your work. One more than that, it's going to double your work. So every time you go up by 1, you double your work in an order 2 to the n. So when we're doing our tasks, when we're writing our programs, usually we want to keep our tasks and using our resources as high up on this range as possible. Okay, so today we're going to talk about a problem, and that problem can be solved it can be solved in these 4 ways. There's 4 different algorithms, but it's the same task. So you have the same task and you can solve it with different algorithms. We're going to go with the shorter ones here, the easier to write but longer, that it takes longer, and we'll go with those today, and then we'll work on more efficient algorithms a little bit later. Okay, so remember that we don't care about constants. So if I go from 0, if I have a for loop, and I do something in here. What is this? What order is this going to be? What family? How does this relate to n? If I double n, it takes,
Double N, it would double the time.
yeah. And what kind of family, what big O is that?
Linear.
Yeah, it's big O of n. So this is big O of n. Now, and let's say I do something, you know, it's like I have one line in here. If I have one line in here, then it's big O of n. What if I had 100 lines in here? It's still big O of n, right? Because we don't care about the constants. If it's 100n or n, I don't know, I don't care. Don't care about the constants. If you double it, double the input, it's gonna double the time that it takes. All right, what about if I have I equals I plus 2 in here? I equals I plus 2. So that's better, right? I don't have to do it as much. It's quicker, right? What family is this in?
Oh, so the same one, right?
Yeah, it's still constant time. It's n over 2. So it doesn't matter if it's 100n or n over 2. I could I plus 10, something like that. But if I do, assume there's something in here. Just put some meat in there so that it indicates something's happening in here. If I were to do this, I equals I times 2, what would that be? If I doubled n,
Would that be the logging time?
yeah. So if I double n, it just takes me one more step. Why? Well, if n is, we're trying to go up to n. If I have n times 2, well, when we get to the old n, then I'm going to be the same number of steps as the old n. Now when I get to the new n, I just have to do one more step through, and it's going to double the iterating variable, okay? So, we got that. Then, I can have doubly nested for loops. Let's just do them. Okay, so we're back to the same, we're used to this. Okay, so we're just incrementing like we normally do with for loops. Then I get another for loop in here. So something has to happen inside the inner for loop. How many times does the outer for loop happen?
N times?
Yeah, the outer for loop happens n time. The inner for loop with the j. Yeah, n times. So, how is the overall running time of this? Overall, it executes n times, so that would be n squared. So we would have an n squared algorithm here. And another thing that you will see quite a bit is now we're going to change this, and we're going to say j equals I, and yeah, okay. So we'll do this. And now j starts at I and goes up to n. So you think about it, okay. When I is 0, this starts at 0 and goes up to n. So the first time through the loop, we've got n, it goes around n times. Now the next time through the loop, I is equal to 1, so j starts at 1 and goes up to n. So we have n minus 1. Third time through the loop, j starts at 2, and it goes up to n, so that's going to be n minus 2. and it's gonna go all the way down to 1. So if we think about it going the other way, this is going to be 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus n minus 1 plus n. And we can come up with a closed form solution to that. That is, the summation is I is equal to 1 to n of I. Yes. So I starts at 1, ends at n. 1 plus 2 plus 3 plus 4 plus. What is the value of this? How do I come up with a closed form solution? So you look it up on the table, right? There's some table at the back of your math book, or you look it up online. Okay, so let's say that n is equal to 6. Yes, so n is let's say that n is equal to 6. This is 1 plus 2 plus 3 plus 4 plus 5 plus 6. Okay, so supposedly Carl Friedrich Gauss, when he was like a misbehaving young boy, was told by his math teacher to keep him busy to add up all the numbers from 0 to 100. And he said, 5,050. What? What? And that is the actual answer. So how did he do it? Well, he recognized that there's a pair of numbers on the end that add up to 7. And there's a pair of numbers next in that add up to 7. And there's a pair of numbers here that add up to 7. So how many pairs are there?
3.
It's 3 in this case. And then if I went out to n, so there's 3 pairs. 6 numbers, 3 pairs. If it were n, if I was going up to n, it would be how many pairs? Yeah, n over 2 pairs, right? Because you take 2 each time. So there's n over 2 pairs. And what is the sum of the pairs? Well, you're always taking 1 on this end and n on the other end. So this was 1 plus 6 gives us 7. But then it would be 1 plus, if I went up to n, it'd be 1 plus n. Okay, so the pairs sum is n plus 1, and there's n over 2 of them. So this is equal to n over 2, that's the number of pairs, times n plus 1. Yep, so that's the closed form solution of it. So what family is this in? Better to go ahead and multiply everything out. It's 1/2 n squared plus n 1/2 n. And with polynomials in big O notation, all we do is we grab the highest order of the polynomial, and we don't care about the constants, and we don't care about the little ones behind. We don't care about any of the lower order polynomials, because you get big enough and it's going to be the n squared term that dominates. So here, all of this ends up being order n squared. When we had the j equals 0, it was order n squared. As a matter of fact, it was exactly n squared steps. Here, it's 1/2 n squared plus 1/2 n steps. Better, faster, doesn't have to do as much, lower time, but still in the same family. Yes?
So what was it when we did I times 2? I
Yeah.
times 2.
When we had I equals I times 2, it ended up being the log n.
Okay.
And that's because I grew really fast. You stop when I gets up to n. But I doubled itself every time to get up to n, and so I grew so fast that there's not many steps that you need of iteration. Okay. Well, I wrote down my example for this, and I left it on my desk. I'm going to try to remember the example, because it's easy to make an example, but it's not easy to make a good one. So let's say that I have this sequence of numbers. Now, think about all the sub-intervals there are, the sub-intervals. We could start at the 1 and end at the 5, and so that's an interval of 3, sub-interval, interval of 3, and sub-interval of 3. And if I chose this sub-interval here, what would be the sum of the numbers? The sum of the numbers in the interval. 1 minus 2 plus 5, it's getting bad. 4, thank you. So when we sum up the elements of that subinterval and we get a 4. Okay? Now the question is, the question posed is, given a sequence of numbers, what is the maximum subinterval where the maximum is determined by adding the numbers together? Okay? And so what is the maximum subinterval? And I'm already looking at this, So it's hard to make a good problem. Oh, it's really hard to make a good problem. Okay, so minus 4, and then this is going to be minus 3. Okay, so, yes. All right, so what is the maximum subinterval? Where does it start and where does it stop? How about just a 1? Nope, that's not going to be good. How about I add them all up? If I add them all up, then if I add them all up, so then I get a 4 and 8, a 5 down goes up to 9, and then, so I get an 8. If I take the whole thing, I get an 8. Does that work? Does that work? Am I correct in saying that if I add up all of them, it's an 8?
Oh, that wasn't adding them.
I thought you were checking my math. I'm not trying to put you on the spot
No, I
here.
was trying to-
I said, it's an 8, and you said, and I thought, what
No.
the, what, did I do something wrong?
No, I was trying to
Figure out how to get the.
Okay, so you're trying to find out the max subinterval.
Yeah.
Okay. Thank you, no problem, I'm sorry, I thought you,
You're good.
I have such low self-esteem that I can't, I always think that I've made a mistake if I, Okay, so if I do the whole thing, it's 8. Okay, what is the actual maximum subinterval?
If you do the first 6, so going up to the 4, well, I guess the second 4.
Say the first 6 up to the second 4?
Yeah. Because after the 4, when you get that minus 3, the 2 after it is not worth that minus 3 to get. But if you get the first neg minus 2, the 5 is worth it, and then the next minus 3, the 4 after it's worth it.
You don't have to start the subinterval at 1, though. Subinterval can be anywhere within.
Oh, it can be anywhere within?
Yeah, it doesn't have to start with a 1.
Well, then never mind. It'd be from 5 to
Yeah,
4.
okay, so I understand why you said that. So this is a subinterval that ends up being the maximum subinterval, and it's just as you said, it's not worth going through the -2 to grasp onto the 1, right?
Mm-hmm.
And likewise, and that's why I did it this way, it's not worth going through the -3 to pick up a 2, that's gonna be a net loss, okay? So in all of this, then, I get a 9, it's a 10, I think? So that's 10. All right. Now, if I wanted to have an algorithm to do this, because maybe I have 100, maybe I have 1,000 different numbers. There's no way you can just squint your eyes and look at 1,000 different numbers and try, oh, I think this will, wait a minute. And the subinterval could be 999 elements, so it could be a very large subinterval. So we need to come up with a methodical way in order to solve this problem. Now that happens to be the correct answer, but we don't really know how we got it other than just, squinting our eyes. We had a heuristic, so you had said that heuristic. The heuristic was can't go through the -3 to get to the 2. But that doesn't translate into a algorithm is a methodical, canned way of just a recipe, you could chunk, do it this way, and it will always work. Question?
No, I was just gonna say, propose like a possible solution.
Okay.
I was thinking maybe it's like, I don't know, like I said, I have no idea how you build this, but you're doing basically an integral, but you're looking at like the next 2 on either side.
Oh, okay. So you start somewhere and you kind of expand out.
Right.
Okay, you can do something like that. Jacob.
Going off that, you could find the largest element in the interval first, and then go from there.
Oh, okay. So you go through, you find the max number. That's order n time. I'm gonna scoot through the entire array, order n. And I find the maximum number, right? And then you start there and work your way out. I don't know that that's always gonna get it. What if I have something like, if 10 is my maximum number, but, way down here, so I got some negative numbers here, and way down here I got a 5, a 6, a 5, a 9,
Right.
another 9. Yeah, I could have a big old meaty chunk down here and just one, like a spike there. So that doesn't necessarily do it. Well, first one, yes.
If you keep track of how much value each, this is a weird, this feels weird, but if you keep track of how much value each negative number has to gain by keeping track of like how many positive elements are on either side of it, that seems like it'd take a while, but not as long as other methods.
Yeah, the way that we're gonna do this first here is gonna take a while, so it's gonna take a while. However, let's go ahead and what I'm gonna do is I am gonna calculate every single sub-interval and its maximum, and its sum, every single sub-interval and the sum of that sub-interval, and then if I do it for every single possible sub-interval, then I'm good. So I'm gonna have, the first one I'm gonna say, starts at 1. And the 0th element, which happens to be 1 in this case. Okay, so I just do a 1. And that's going to be equal to 1. Actually, I'll put it over here. So 1, hey, that's my new maximum interval that I have seen so far, is a 1. Count them, 1, Then I could have a 1 plus a minus 2. Okay, 1 plus a minus 2 is minus 1. Doesn't help. Now I don't give up at this point, because I still need to keep on going through here. So I could have a 1 plus a negative 2 plus a 5. Okay, and that is equal to 4, I think. Then I can have a 1 plus a negative 2 plus a 5 plus a 4. Okay, that gives me an 8. And this is minus 2, of course. Then I can have a 1 plus negative 2 plus a 5 plus a 4 plus a minus 3. And there I